welcome everybody. And what I'm going to do is show how the rapid deformation and morphing capability that Sculptor has can be harnessed as part of a process integration and design optimization workflow that Mike introduced. So, and we'll use that to quickly generate a design of experiments, run an optimization, and then ultimately distribute that information about the CFD analysis to a much larger audience, so that you're really able to get much higher value out of the analysis that you've run. So throughout the case study that we'll show you today, we're going to demonstrate really how Sculptor and Optimus can help save you time by removing the need to recad and to remesh for each design change, and how an automated workflow can reduce the amount of user input that's needed for complex tasks. We'll show you how using Sculptor and Optimus can help you improve the performance of your products by making subtle shape changes to your geometry, and by using Optimus's intelligent optimization methods. And then finally, we'll show that you can use Sculptor and Optimus to consolidate the knowledge that you're able to gain from the optimization and analysis cycle. You can then, as I mentioned before, distribute that intellectual property through Excel so that non-CFD users can access and create new simulations quickly. The case study that we'll show today focuses on blades. These blades are generally located inside of a jet engine, as you can see in the top image. These blades can get damaged from a number of environmental sources. There's over 26 million blades that are in use throughout the world today. A great deal of time and money is spent repairing damaged blades. And so when these blades are damaged, what's called a blend is used to fix the blades. So it's really imperative to determine the maximum amount of damage that a blade can have and still provide enough lift force to keep the jet engine in balance. Here are a few examples of damage that can occur to these blades. So the damage is referred to as a foreign object damage, or FOD, and it's generally referred to as a nick. So that's what we'll be talking about and simulating today. So our goal in the case study is to simulate the FODs that occur on the blade and to calculate the aerodynamic lift force so that we can eventually find the largest nick that a blade can have and still provide enough lift force to keep the jet engine in balance. The process that we're going to go through in order to do that is that we'll first determine the input and output variables that are needed to control the blade and to also get the information that we need from the blade. We will then use that information to create an automated workflow inside of Optimus. That workflow will drive a design of experiments, and then the DOE response data will be used to create what's referred to as a response surface model, or a mathematical approximation of our design space. We'll use that response surface model as part of an optimization that will run much faster than the original design of experiments ran. So from all of that, we will we'll generate some, or we'll consolidate some corporate knowledge so that we can distribute the intellectual property about the model to a large number of users that otherwise would not have been able to access that data. So as I mentioned, the first step is to determine the variables. So we have input variables and output variables, obviously. And as you saw in Mark's presentation, he's used the arbitrary shape deformation ability of Sculptor to create or to simulate nicks that occur on the leading edge of the blade. And so what we've done is we've actually created 4 separate nick locations along that leading edge, kind of growing in an axial direction along the blade. So those will be our input variables, those 4 different nick locations. So and then the output variables, the information that we need to get from the analysis, from the CFD analysis, is the lift force that's being generated by that blade. And then also from Sculptor, we will calculate the volume of the blade. So our next step is to determine the workflow. We first want to change the geometry, calculate the volume, and then export the morphed mesh. After that, we want to determine if the mesh quality is good enough to allow us to run a simulation. And then finally, we want to solve the model in our CFD analysis tool and then extract the outputs from the reports that are generated by the analysis tool. And for this optimization, we've selected STAR-CCM Plus as our CFD analysis tool. Optimus has built-in dialogues for CCM Plus and really all the other numerical analysis tools out there, including Fluent and CFX, OpenFoam, and even in-house codes that are developed internally. So the dialogues that Optimus has generated automatically detect both the input and the output variables that are inside of the input files for the CFD tools. And then Optimus, of course, also has built-in dialogues for Sculptor that we'll use. So now we'll show the workflow as it's actually been created inside of Optimus. So you'll remember that the first step was to change the geometry, calculate the volume, and export the morphed mesh. So here you can see the call to Sculptor, kind of in the middle of that image there, and then the green boxes that are the input and output files that Sculptor needs to make the deformation. The teal box or the teal oval in the upper left is actually the input variables that are used to make the changes to Sculptor, to the blade inside of Sculptor, and then the red shape at the bottom is actually an output variable that comes from one of the Sculptor logs. And in this case, it's the volume variable. Now, the next step is to check the mesh inside of CCM Plus to determine the quality. This could have been done, as Mark said, inside of Sculptor, but we added this extra step to do the check natively inside of CCM Plus. And finally, if the mesh quality is valid, we're actually able to use Optimus to make a decision about if we should move forward with the analysis or if we should generate a fail condition. So, and then finally, the red oval in the bottom right is where we extract the outputs from the CFD analysis logs. Now, after we've automated the workflow setup, we're actually ready to begin the design of experiments. So the reason that we need to define a design of experiments is so that we can in a statistically relevant way, cover the entire design space. So we need to cover the entire design space with experiments so that we can create the response surface model that we've been talking about. So this will all help to support the design exploration down the road. So for this case, we've actually determined to use the Latin hypercube design of experiments method. Inside of Optimus, the Latin hypercube is one of about 20 different DOE methods, including a full factorial method, a custom adjustable factorial method, and a Monte Carlo method. Now, we ran the DOE. Each of the individual CFD experiments took about about an hour to solve. And we ran 100 different designs as part of our DOE. So here you can see the results of those 100 experiments. You'll notice here that there's really good input distribution amongst the input variables, the FOD 1, 2, 3, and 4. And as well, you'll notice that some trends are beginning to emerge in these two columns, which are the volume and the force output columns. The chart on the right shows both the lift force response for the baseline geometry in green there, and then the response for each of the additional 100 experiments in blue. Now, the video that's being shown on your screen is actually a video that's exported from Sculptor, and it shows each of the different deformations that were part of the design of experiments. So these are all 100 designs that were tested inside of our CFD tool. So from all of this response data, we're actually able to generate some correlation. Using tools inside of Optimus, we were able to find the influence that each input variable had on the output variables. And in addition, we were able to find the correlation that the output variables had on each other. So we've identified that the variables FOD2 and 3 had the strongest correlation with lift force, and that FOD1 and 4 had the weakest correlation with lift force. The correlation, though, or the influence that FOD1 and 4 had on the lift force was still relatively high. You'll notice that it's not that many points off of FOD2 and 3. And so unlike in the example that Mike showed earlier, for the optimization, we actually won't be able to exclude any of the 4 input variables. So we need to keep all 4 input variables as part of our optimization. So in addition, we did notice that the lift force and the volume output variables were highly correlated. So if you're keeping track, the next step in our process was to create a response surface model from the data that we've generated, or from the DOE data that we've generated. Now, a response surface model, for those of you that may not be familiar with it, is simply a mathematical approximation of a set of data points. Most have used the add trendline function in Excel to create a mathematical approximation of a two-dimensional data set, as you can see on the screen here. The trendline equation that we've all added to the chart in the past is, in fact, the mathematical approximation of the data. Optimus has the ability to quickly create a multi-dimensional mathematical approximation that includes multiple inputs and outputs. Obviously, it's a little more difficult to visualize than the 2D mathematical approximation here inside of Excel. So I'm going to switch over to Optimus now, so that for the first time you can see the user interface of Optimus. Here we can see the response data from the 100 design of experiment runs that were calculated, the volume and the lift force there. And now, as we'll show, we can create that response surface model with 2 clicks. So we'll select the type of response surface that we want. In this case, we'll do a radial basis function as the formula to calculate our response surface, and then simply click Apply. And here in about 5 seconds or so, that response surface will in fact be generated. So it took 8 seconds, excuse me. And now you can see it shows up in our tree as Model 1. We can then visualize this response surface. So as I mentioned, it's not the simple line which we had in Excel, but it's actually a much more complex surface. So this is, in fact, the response surface model that's been generated. So there we're comparing outputs, here we're comparing the lift force output to the FOD1 and FOD2 input variables. So we mentioned before that FOD3 and FOD4 had the FOD3 and FOD2 had the highest influence on the lift force. So here we can see the response surface that's generated from that data. Now the beauty of this response surface is we can now calculate points along this surface much faster than we could by going out and calling the CFD analysis tool. So here we'll just run 100 new experiments. So these are experiments that have not been previously solved in the CFD analysis. And we'll run these experiments, and you'll see that in just a second, 100 new designs were able to be calculated. So for the optimization, we want to find the largest NIC that can be created that will still maintain a feasible lift force. So Optimus, again, has a number of optimization methods, but we've selected the simulated annealing method due to its ability to cover the optimization path extremely well and test for a global optimum. We've set a constraint on the lift force at a 1% reduction in the baseline lift force, and we want to minimize volume, which essentially allows us to find the largest NIC that we can deal with, that we can have. So here you see the progression of the optimization. So the actual optimization took less than 2 seconds on that response surface model. And you can see that we were able to quickly converge on an optimal solution. That is the pink vertical line in the chart. We were able to reduce the volume by about 4 points, which is much larger, actually, than we expected. So, and you'll notice also that the optimization actually went beyond the constraint in order to determine if a global minimum had been identified. And here's the resultant geometry that was created for the optimal solution. Now, the next step in our process is to consolidate corporate knowledge. So the concept here is now to allow other non-CFD users to access and extend the data that was calculated with the DOE and the optimization. So Optimus allows the users to export the response surface from Optimus and load it, in this case, into Excel. So here you can see that the user has defined, I think we've got 30 unique experiments inside of Excel. This is the data that you see in the red column. These experiments are ones that were not previously calculated in the CFD tool. And I'll just make a few changes to these experiments. Then the user simply has to hit calculate, and Excel will, using the Win32com app and connecting to that exported response surface, call the response surface model and generate the results that you can see have occurred, and then we've plotted them here. So any Excel dashboard could be made here to interact with that response surface model. All right, so what have we seen here? Let's discuss the impact a little bit. So without Sculptor and Optimus, the design of experiments and the optimization would have taken about 17,000 minutes. With Sculptor and Optimus, it only took about 6,300 minutes. So over 150 hours were saved. And here's how we got those. Here's how we got those numbers. You can see, obviously, some significant time savings in the creation of the geometry with Sculptor, removing the need to recad and remesh, and then also in the simulation time during the optimization step. And really, this process would not have been possible without Sculptor and Optimus. It would have been impractical to make all of those design changes, and it would have been impossible to drive the optimization and to export the data to Excel when we were done. So we've shown now that with Sculptor and Optimus, over 38 man-hours, or a week of time, was saved. And with Optimus, over 140 computer hours simulation time was saved. And Sculptor enabled the generation of thousands of different designs, really. And then Optimus found the maximum acceptable FOD. And ultimately, we showed how the simulated designs can be extracted or can be changed by non-CFD users inside of Excel, and the complex CFD models were able to be solved in seconds. So in conclusion, with Sculptor, we removed the need to recad and to remesh, and we were able, with Optimus, to determine the maximum FOD size that we could have. And then finally, we were able to get non-CFD users fast and easy access to the data.